Alright guys, today we're going to take a look at integration with natural logs. Last couple of days we've been looking at derivatives and doing all the things that we learned with derivatives with natural logs. And now the next couple of days we're going to look at integration. Now the nice thing about integration with natural logs is it's pretty much just the opposite of what we did with derivatives. So if you remember that our derivative for the natural log of x was 1 over x. Well, the integral is just going to be the opposite. The integral of 1 over x dx is going to be the natural log of the absolute value of x plus c. Now, the only difference is we do have absolute value around the x. That's really important because of the sign issues. Remember, natural logs can only have a domain of 0 to infinity. 1 over x could have any domain. Okay, we can put any number in for this x versus this one, we are limited to positive numbers. So we have to have that absolute value around the x when we integrate. All right, now in most cases we are going to deal with u substitution. Okay, and again, we're looking for that stuff inside of there. So whenever you get something where you have that u prime over u, we got to look for u substitution, which would give us natural log absolute value of u plus c. Okay, so it's really just working backwards and using those integration techniques that we learned back in chapter 4. All right, we're going to take a look at a couple examples today and see how this works out. All right, starting off, first example, we got integral of 2 over x dx. Now, I got this 2 up top here. Now remember, 2 is actually just a constant being multiplied by 1 over x. And so since it's a constant, we can actually pull it out of the integral. And there we have that integral of just 1 over x dx, which again is going to give us just natural log absolute value of x plus c. Okay, that's one of our more basic ones. Let's try one that actually has some u substitution going in with it. Let's take a look at the integral of 1 over 4x minus 1. All right, notice we still have this fraction 1 over something. All right, and our something is stuff. We have more than just x there. So anytime we have that stuff in the denominator, we do have to go ahead and do u substitution. So in this case, we have u equals that stuff, 4x minus 1. So let's go ahead and do u substitution. We're going to take the derivative of u. Derivative of 4x minus 1, we get 4 dx. Now remember, what we were trying to do is substitute in du here. So we have a dx, but we don't have a 4. And since we don't have a 4, we're going to have to go ahead and bring this 4 over as 1/4 du equals dx. So now we can go and substitute this in. We can replace the 4x minus 1 with u, and the dx can be replaced with 1/4 du. Now that 1/4, because it's a constant, I can just bring it out. And here what I have is 1 over u du. Well, that's just our natural log of u. So natural log absolute value of u plus c. All right, but remember, u means unfinished, so we want to make sure we do substitute that u back in. So 1/4 natural log absolute value of u was 4x minus 1. Let's put that in there. 4x minus 1 plus c. All right, and that'd be our final answer with that one. All right, so again, we're looking for that stuff in the bottom. Now, you got to make sure you keep an eye out because not every fraction is going to be natural log. The key here is that whatever is in the denominator is raised to the first power. If you look at our power rule back from chapter 4, we never addressed the idea of something over something to the first power. We always had like 1 over x squared or 1 over x to the third or 1 over square root of x even. we never dealt with 1 over x to the first power, and that's because it's natural log. So we're looking for that term in the bottom that's raised to the first power. That's going to give us an idea that it is natural log. All right, now whenever we're doing natural log, we also want to be on the lookout for that u prime over u. If we see something that's already in the form of u prime over u, we really don't have to do u substitution with it. It's already there for us. All right, so we want to be able to recognize u prime over u. All right, when you can recognize that, it just makes it a lot quicker. For example, all right, 3x squared plus 1 over x cubed plus x. If you notice here, yeah, x cubed plus x in the denominator. Well, if you take the derivative of x cubed plus x, you get 3x squared plus 1. This is that u prime over u. All right, even if you try to do u substitution, u would be x cubed plus x. You get 3x squared plus 1 dx. Well, there it is up top. And so when you see that, you can go right to natural log, absolute value of u, x cubed plus x plus c. All right. Another example real quick, same idea. If you had, let's throw a little trig in there. Secant squared x over tangent of x dx. Don't get freaked out by all the trig. All right, if you recognize that, hey, the derivative of tangent is secant squared. Well, that's u prime over u again. So this is just going to be natural log of u tangent plus c. So when you do have cases where it's just u prime over u, we can jump right to natural log of u plus c, or absolute value of u plus c. All right, one of the big things that we do see with natural log, antiderivatives, is using a little long division. All right, whenever you have a situation where the numerator has the same degree or a higher degree than the denominator, we have to use long division. All right. So again, whenever the degree is higher or equal to the degree of the denominator. Really, I should say the degree of the numerator is higher or equal to the degree of the denominator, we have to simplify by using long division. Now, some of you are thinking, well, can I use synthetic division? Yes, only in the cases that you can use synthetic division. Remember, synthetic division is specific to only when you have x plus or minus a term in the denominator. All right, long division tends to be the case we use a lot more often. All right, so let me give you an example here. That we have the integral of x squared plus x plus 1 divided by x plus 1 dx. Now this is a case where the degrees are the same. Okay, and a lot of times we only remember when the degree is higher, use long division, but even if they're the same, unless we can simplify it somehow, we have to use long division. So we're going to go ahead and use long division to simplify this out a little bit. So we have x plus 1 into x squared plus x plus 1. So we've got to remember those rules of long division. We're going to take that x, and what do I have to multiply x by to get x squared? We have to multiply it by x. Put the x up there, I'm going to multiply and get x squared. Now, here I get plus x. I subtract. All right, when I go ahead and subtract that, I end up canceling both of these out, which leaves me with just 1. So these cancel, and then I can bring down that 1, and all I have is 1 left. Now, x doesn't go into 1. So here, this is my remainder. This is the quotient. And we actually have to rewrite this, and we're going to rewrite this integral now as a new integral of x. I realize I just wrote the wrong problem down. This should be x squared. So let's fix that real quick. That makes the problem a little bit different. All right, replace that. That's why you always want to be careful. Copy down the right problem. All right, now let's try that again. X squared into x squared is 1. Makes a little bit of a difference because now I get x squared plus 1. I'm going to put that plus 1 over here. And then subtract this and this cancel out, bringing down just an x. Now, x is my remainder. That's better. And 1 is the quotient. So when I rewrite this, I actually have 1 plus whatever your remainder is. You're going to take that remainder and put it over the divisors. So x over x squared plus 1. And now what we've done is we now have a new integral that we can actually evaluate. Okay? So with these two, we have some natural log stuff going on here. Let's go ahead and get us a little bit more room. All right, integrate 1, nice and easy. Okay, but this x over x squared plus 1, this is the case where we're going to have to do some u substitution. So what I'm actually going to do is split this into 2 different integrals. I'm going to do the integral of 1 dx plus the integral of x over x squared plus 1 dx. That's going to allow us to go ahead and do u substitution with this one and not have to get confused with the u substitution with this part. All right, let me move it over here. We know the antiderivative of 1 is just x. So x. Over on this part, we have x over x squared plus 1 dx. We got that stuff in the bottom, so let's do u substitution. All right, u equals x squared plus 1. du is going to be 2x dx. Now, if you look, I have the x dx right here. I'm missing the 2, so I'm going to bring the 2 over as 1/2 du equals x dx. And then I'm going to go ahead and put that out front. So now I have x plus 1/2. All right, this is getting replaced, so I got 1 over u du. That 1 over u du is that natural log of absolute value of u plus c. Now I can replace u. So my final answer becomes x plus 1/2. Natural log, u again was x squared plus 1. And plus c. And that ends up being our final answer for this problem. All right, so whenever, again, recap, whenever the degree is higher or the same in the numerator as in the denominator, we have to do long division. Simplify it, and we're going to take that answer, all right, the quotient plus the remainder over the divisor, which was right here, and integrate our new simplified function there. All right, and typically we'll get some natural logs out of that. All right, a couple more examples. All right, a little bit harder example, whenever we have that extra variable in there. All right, whenever we have that extra variable, we have to change some variables. All right, so now we have an example with All right, 2x over x plus 1 squared. So this looks similar to what we did back in chapter 4. We have something raised to the second power in the bottom. Well, let's think back how we did this back in chapter 4. We're going to make our u equal to the stuff. U equals x plus 1. du is going to equal dx. The problem is we have that extra variable up there, that extra x. And whenever we have that extra x, we have to solve for x. So x becomes u minus 1. Now let's go ahead and replace what we know. So now we have, write it over here, integral of 2 times x is u minus 1. All right, x plus 1 is u, so I'm going to do u squared on the bottom. And then dx is equal to du. Well, now I have another problem. I have this up top with a single term in the bottom. And remember what we do with single terms in the bottom. Whenever you have a single term in the bottom, split it up into multiple fractions. So first I'm going to simplify this by multiplying by 2. Distribute to get 2u minus 2. And then I'm going to split it into multiple fractions. So 2u over u squared minus 2 over u squared du. Well, now I can simplify exponents. So here I have 2u over u squared. So that's going to simplify to 2 over u minus 2 over u squared du. Well, the first one ends up working out to be our natural log. Remember, 2 over u just works out to be 2 natural log of u. And if you think back to chapter 4 here, this we can rewrite as negative 2u to the negative second power. So we can use power rule. And when we use power rule, that's actually going to give us plus 2 over u plus c. And of course, we have to finish it out with putting in u in there, so I'm going to go ahead and put that up here. We have 2 natural log. U again was x plus 1, back to our original. All right, and then 2, so actually I'm going to run out of room, and then plus c. Okay, so this is where we have to change variables in. So anytime we have that extra x or extra whatever variable we have there. All right, perfect. All right, last examples. One thing that we haven't talked about is what is the actual antiderivative of natural log of u, or natural log of x? Well, you're not going to learn that till you get to BC. Okay, that's a BC topic because it's something that we deal with integration by parts. So for now, whenever you see an integral with natural log of x, since we don't know what the integral is for that yet, make that your u. All right, since we don't know integral of natural log of x yet, make u equal natural log of x and see what happens. So let's take a look at this example here. Integral of 1 over x natural log of x dx. Now again, we have this natural log of x. Anytime you see that natural log of x there, let's make that equal to our u. So u equals natural log of x. All right, well du, take the derivative 1 over x dx. Well, remember this right here, if I were to rewrite it so you can see it a little bit better, is just 1 over x times 1 over natural log of x dx. And so 1 over x dx is right there. It's already in our problem. So now I can rewrite this as 1 over u du. Well, antiderivative of 1 over u du is that natural log, absolute value of u plus c. And now we can put our u back in there, and our u is just natural log of x. So natural log, absolute value of the natural log of x plus c. It's pretty common to end up with 2 natural logs, or a natural log within a natural log, when you have a natural log in your integral. Okay, so that's pretty much all the examples of integrals we have today. Again, you want to make sure you know the rule for integrating just natural log of x. Look out for that u prime over u. That happens a lot. Watch for the powers. If the powers are higher or equal to in the numerator than as in the denominator, we have to use long division. And then watch for the changing variables. And lastly, if you get that natural log of x in there, go ahead and use that as your u, and that should set you up for u substitution. All right, so that should set you up well for your homework tonight. Okay.